What we have seen so far is the loads that are acting on aircraft and spacecraft. These loads can introduce deformations in the structure that correlate to stresses within the structure. We'll take a closer look at 3 different load cases and how they translate into stresses and strain in a structure we will analyze. When we know the stresses in a structure, we can assess whether the materials used in the structure are capable to sustain these loads. In this lecture, I want to focus on the first loading case, a specific loading of the fuselage, pressurization, and more specifically on how this loading translates into stresses in the fuselage. To evaluate the stresses in the fuselage due to pressurization, we first simplify the fuselage to a cylindrical, thin-walled pressure vessel, where a pressure is applied on the inner surface. Due to this pressure, there will be circumferential stresses and longitudinal stresses. We can calculate these stresses via equilibrium equations. As can be seen, the circumferential stresses are dependent on the pressure difference between the inside of the aircraft and the outside, namely delta P, the radius r, and the thickness of the fuselage shell T. Also, the longitudinal stresses can be derived from equilibrium and also depend on the pressure difference, radius, and thickness of the vessel. If we relate the stresses in the longitudinal and circumferential direction, we can see that the circumferential stress is twice the longitudinal stress. From these stresses and their relation to each other, we can now derive the strains due to pressurization in circumferential and longitudinal direction by applying Hooke's law for the biaxial stress condition. They are both dependent on the Young's modulus and the Poisson ratio of the material chosen for the fuselage. Let's assume we have a metallic pressure vessel, thus having a Poisson ratio of about 0.3. We can then find the relationship between the circumferential and longitudinal strain. The circumferential strain is 4.25 times larger than the longitudinal strain. Now we make our structure a bit more representative for a real metallic fuselage structure. We add frames and the transition from a tubular shape to the spherical end sections. What are the implications by adding these features? Let's first look at the spherical end sections and how they affect the design of the fuselage. We then first need to know the stress and strain due to pressurization in a pressurized sphere. The stresses in both directions are the same, and the strains are the same in all directions. So what do we need at the connection of the cylindrical and spherical section? We want the strains in circumferential direction at the connection to be equal to each other. And we also want the radius of the sphere to be equal to the radius of the cylinder. This way, we can avoid discontinuities in a structure. So what does that mean for our structure? Can we then say something about the thickness both sections need to have at the connection? Let's use the relations for the strains we have derived previously. We put the strain present in a sphere equal to the circumferential strain of the cylindrical part. Then what we can derive is that the thickness of the skin of the cylindrical part needs to be around 2.5 times larger than the thickness of the spherical part. Everything we have derived so far is for a very simplified fuselage structure. In reality, the thickness of the fuselage is not constant. There are stringers and frame present to maintain the aerodynamic shape. There are local reinforcements at the cutouts. They will all have an influence on the stress distribution in our structure. The frames, for instance, have a significant impact on the deformation of the pressurized fuselage and on the circumferential stresses. The deformation near the frames is limited, so you get a pillowing effect due to the addition of frames. I want to cover one more aspect on the fuselage pressurization. How do the designers establish the pressure load case for the fuselage pressurization? First of all, failure of a fuselage structure under pressure may imply a disastrous occurrence, like an exploding balloon. The designers therefore apply a high safety factor of 2. The pressure difference they designed for is the pressure in the cabin minus the air pressure on the height they are flying. The cabin pressure is set to a pressure which is still comfortable for the passengers, typically related to an altitude between 2,400 and 3,000 meters instead of sea level, to decrease the design pressure difference for the cruise altitude. What we have seen today is that the pressurization of the fuselage causes circumferential and longitudinal stresses and strains. You have learned the relationships between the applied pressure difference and these stresses and strains of a simplified fuselage structure. You also have taken a look at the design of a real fuselage structure, including frames and design pressures.